Hello, this is our new unit on logic. So although this is mathematics, you may not feel like that you're doing mathematics in this unit, and a lot of students are really excited about this particular unit that we're starting. The first topic in this unit is Venn diagrams. So we've worked with Venn diagrams when we worked with quadrilaterals, and when we studied quadrilaterals, we knew that every single square was a special type of parallelogram, which means for the Venn diagram, we could say this. And what this means is every square is a parallelogram. It also means that there are objects out here that are not squares, but they are considered parallelograms. So that's the basics of a Venn diagram. So all we're doing with a Venn diagram is we are representing the relationships between various sets. They are also used in conditional statements. A conditional statement is an if-then statement. If you study, then you will pass the test. So if we look at the example over here, all high school students take geometry. So you can see the Venn diagram that we have, and if we take all of the high school students, every single one of them is inside the circle for people who take geometry. So that means there are people out here who aren't high school students who are taking geometry, perhaps a middle school student, perhaps a student in college, but all the high school students are people who will take geometry. So the small circle represents the all, and the big circle represents what they all do. So we have a subset right here. The set of high school students is a subset of the people taking geometry. It's a set within a set. We also can say, when we read this Venn diagram, typically we say, all high school students take geometry. We can also convert that into the conditional form, which is the if-then form, which would be read as, if a person is a high school student, then he or she is taking geometry. So both of the things I have underlined represent that Venn diagram that we have about high school students and people taking geometry. So moving on, we're going to try a couple. So for each of the following statements, create a Venn diagram and then convert the statement into if-then form. So I would like for you right now to go ahead and try and draw number 1. Every cat has a tail. So please go ahead and draw the Venn diagram for number 1 now. Okay, so every cat has a tail means all your cats have to be inside of the circle that you could just write tails, but I would say animals with tails. And that's what your Venn diagram is going to look like. And again, we can write this in if-then form. The if is going to be the red part. The then is going to be the black part. So the if part is always the small circle on the inside. So, sorry about that. So the if is a small circle inside. So if an animal is a cat, then what do I have to know about this cat? Then it has a tail. So moving on to the next one. All whole numbers are integers, which means what goes the red part that goes on the inside? That's the all, and that's my whole numbers. So I have whole numbers. And I know that all my whole numbers are integers. So here's my Venn diagram. Now I need to turn this into an if-then statement. If a number, and where am I going to start? I'm going to start with the red small circle inside, is a whole number, then I know the outside that's in black. Then it is an integer. Now at this point, if you need more time to write that down, please pause the video here so that you may write that entire statement down before moving on to number 3. So what I would like for you to do for number 3, I would like for you to pause the video and complete all of number 3. I want the Venn diagram with the if-then statement. So go ahead and pause your video now, please. Here is my solution to number 3. The small circle is live in Idaho. The large circle outside is like potatoes, and the if-then statement is if a person lives in Idaho, then he likes potatoes. If you did not get that correct, please pause the video here so that you can make corrections to your paper. Now moving on to number 4, I'd again would like for you to pause the video and complete all of number 4. So please pause the video now. Here is my solution for number 4. Again, if you did not get this correct, I would like for you to pause the video and make corrections. My small circle inside is athletes, the large circle outside is allowed in the weight room. My if-then statement is if a person is an athlete, then she is allowed in the weight room. Now I wrote she because I think she should be allowed in the weight room, but if you wrote he, that's fabulous, as long as we have the same idea in our statement. So moving on to the next page. We have 3 main different ways to represent Venn diagrams. The one that we worked with was this first one, and the first one is an all. That means all of one set is within another set. So when we said all cats have tails, we drew something that looked like this very first Venn diagram. The next kind that we have is sum, and the sum is represented by where 2 sets overlap. What that means is these things that are in P don't have all of the characteristics that are in Q. And these things over here that are in Q don't have all the characteristics of the things that are in P. However, when we talk about these things in the middle in that football shape, those things that I've marked R, those things have all the characteristics of the P set as well as all the characteristics of the Y set. So when we say some elements, we mean where 2 sets overlap. Then the last kind that we have is called none. If 2 sets have nothing in common, then we would write them in 2 separate circles or diagrams where they wouldn't touch. So for example, if we were talking about circles and squares, they don't have anything in common, so they would have their own circles where they would not touch. So now we're going to be talking about more than just 2 sets. On the front, we were only dealing with 2 things. Now we're going to be dealing with 3 or more. So this Venn diagram represents the relationship between goats, farm animals, and pigs. So looking at this, what do we know about the goats and the pigs? Well, there are no goats that are pigs, and that makes sense. Now, are there some goats that are farm animals? And yes, we have some goats that are farm animals right here. Now, we also have some pigs that are farm animals. So we have pigs that are farm animals. We also have these pigs out here. These are not farm animals. These are wild pigs, or they don't live on a farm. Maybe they're in the zoo. And these goats over here, those goats are maybe wild goats, or they live in the zoo, but they don't live on the farm. And what's also interesting is we've got all these animals over here that are farm animals, but these animals are not pigs, and they're not goats. Maybe they're cows. So here's a relationship between farm animals, goats, and pigs. So with that idea, we're going to go on to create Venn diagrams for these situations. So dogs, puppies, and animals. And let me clarify what I mean by puppies. A puppy is a baby dog. So every single puppy is a certain kind of dog. So we're going to go ahead and put all the puppies, first and foremost, have to be inside of the dogs. Because again, every single puppy is just a baby dog. So every single puppy has to be inside the dog circle. And what do we know? What's the relationship between dogs and animals? Are there dogs that are not animals? Are some dogs animals, or are all dogs animals? And all dogs are animals, which means we need to have circle on the outside of both of them where all the animals are. So that means that every single dog is an animal, which means every single puppy is an animal, but it also means there are some animals that are not dogs. So let's look at number 6, basketball players, musicians, and girls. So are all girls musicians? No, not necessarily. Are all girls basketball players? No, not necessarily. Are all musicians girls? No. Are all musicians basketball players? No. Are all basketball players musicians? No. And are all basketball players girls? No. So we don't have an all anywhere. So let's move on to maybe some or none. Are there some basketball players that are girls? And I would say yes. We have some basketball players. And I would say some of them are girls. So you can see that those two circles have overlapped. I have a region where there are basketball players that are girls, and I have a region of basketball players that are not girls. So where does musicians fit in? Could there be basketball players that are musicians? I think so. Could there be girls that are musicians? I think so too, which means my next circle can't just intersect with the green basketball players, and it can't just intersect with the red girls. It's got to intersect with both of them. So my musicians are actually going to go right here. So that means I have some musicians that are girls, I have some musicians that are basketball players, and I have some musicians that are girls and basketball players. So here's our relationship between basketball players, musicians, and girls. Again, if you've got any questions, go ahead and jot them down right here on the paper so you can bring them into your teacher. Number 7, rabbits, bunnies, wolves, and mammals. I would like for you to try and draw this one. Please remember that all bunnies are baby rabbits. So pause the video now and complete number 7, please. This is what I have. All of my bunnies are inside of my rabbit circle. My wolf circle, don't touch my rabbits because there aren't any wolves that are rabbits, but the wolves and the rabbits are both within the mammal circle, and it leaves space for there to be mammals that aren't rabbits and aren't wolves. Now, in number 8, I just want to talk about number 8. This is what most people say. They say that all sons are fathers and that all fathers are grandfathers. I'm just going to write grandfathers like this. So this is what most people say. But let's think about what this is saying. Someone you know is someone's son. So think about your brother or a friend that you have in class who is a boy, because that makes them a son. So I'm going to call that person Al. So Al is going to go right here. What does this mean? This means that Al is someone's son. It means Al is also someone's father. And more importantly, Al is apparently someone's grandfather. Now, is it really possible that your brother or your friend in school is a father and a grandfather right now? And no, that doesn't actually make any sense. So this is not how we write the relationship between sons, fathers, and grandfathers. Let's now talk about how we really do. What do we know about every single grandfather? In order to become a grandfather, the first thing you had to be was a father. So every single grandfather has to be someone's father. And before you were ever someone's father, you had to be someone's child, someone's son. So this is our relationship between sons, fathers, and grandfathers. Hopefully that makes sense. Moving on to the next page. Now we're going to talk about intersection and union. We've actually already done this with our Venn diagrams. I'm just introducing a new word. So when we combine all of the elements, that's called a union. Union of two sets is everybody that's in even one of the sets. So at this point, we're going to also talk about, we're going to look at this example. So if set A was 1, 2, 3, 4, 5, set B were the numbers 2, 4, 6, and you can see this Venn diagram we have here. 2 and 4 are in both of the sets, so they are in the overlapping area between A and B. 6 is only in B, so it's off to the side, and 1, 3, and 5 are only in A, so that's off to the side. The union of these two sets is all of the numbers that we have in both of the sets combined. So the union is going to be 1, 2, 3, 4, 5, 6, which is right here. So it's everybody. The union means everybody. So let's look at our practice. Shade A, union B. So my question is, what does C have to do with anything? Absolutely nothing. So when we shade this, we're going to shade everybody that's in A. And once we've shaded everybody that's in A, it doesn't have to be pretty, we're going to shade everybody that's in B. Now, did we shade some of C? Yeah, but C really wasn't relevant to what I was doing. So let's look at number 2. You're going to shade A, union B, union C. So I'm taking A, unioning it with B, and unioning it with C, which means everyone gets to be shaded in. So we have A, we're going to have B, and we're going to have C. And everyone's going to be shaded in. So that's the union. However many sets you have, you're just going to shade everyone. Everyone's going to be included. On to the next page. The next page is the intersection. And the intersection of two sets, that's going to be where the common elements are. The intersection is the common elements. Oh, and sorry, can we back up one page? I didn't mention the notation, which I think is written here. This notation right here means A union B. Otherwise, it's also known as A or B. So anything in A or anything in B. I apologize, back to where we were. So this one is called an AND statement. So it's anything that is in both A and B. And if you look at the notation here, this notation means A intersect B, and it also means A and B, which means the elements must be in A and at the same time be in B. So we have set A is 1, 2, 3, 7, 11, 13. B is 1, 4, 7, 10, 13, 17. The common elements, the ones that are in both, are 1, 7, and 13. So where I have shaded is the intersection of the two sets. It's also called where A and B intersect. Sometimes we'll have nothing in the intersection, and that would be called the empty set or the null set. So let's look at number 1. Shade A intersect C. So I want to know, where does A intersect with C? And when you draw them in, you should see a little football shape where they intersect, and that is the part we should shade, where the two sets intersect. So moving on to number 2, this one we want to shade A intersect B intersect C. So I've got A right here, I've got B over here. So right now I've got a football where A and B meet. However, I want to know where A, B, and C all meet. So now, if you look at this, it's where all of them meet. And this little tiny region is more of a triangular region. Right in here. I don't know if I can shade it very well. So when I have 3 sets intersecting, I now have a triangular region where they intersect. So this first one is where they're both in A and B, and number 2, all the elements that are in A and B and C all at the same time. So again, bring any questions that you have to class, and I hope you have a wonderful evening.